Welcome to Study Loop.
In this exercise, we have an anisotropic three-dimensional harmonic oscillator whose potential is given by this formula here. U of x, y, and z is equal to 1/2 of k1 times x2 plus x plus y2 plus 1/2 of k2 times z squared. Notice that the harmonic oscillator is anisotropic in this case because the force constant k1 for the x and y directions is different from the force constant k2. In fact, k1 is greater than k2. This is imposed by the exercise. In question A, we have to find a general expression for the energies of this 3D harmonic oscillator. So basically, I'm going to take a solution psi of x, y, and z to be the multiplication of a function of x times a function of y times a function of z. This is my attempt of solution. And I'm going to take both the function of x, the function of y, and the function of z to be themselves solutions to the one-dimensional Schrodinger equation for the harmonic oscillator. So basically, they obey the following equation. So x squared divided minus x squared, minus h bar squared divided by 2m times derivative of x with respect the derivative of psi with respect to x plus 1/2 of k1 x squared times psi of n x squared is equal to e times psi of nx, where e is equal to h bar omega times nx plus 1/2, with omega being equal to the square root of k over m. Okay. The same thing for ny. Sorry, there should be a 1 here. The same thing for psi of ny and for psi of nz. The only difference for psi of nz is that instead of k1, we will have k2 in all the terms here. So basically, I'm going to use Schrodinger's equation to find what is the energy of this 3D wave function. So we have h bar squared divided by 2m times d2 dx2 plus d2 dy2 plus d2 dz2 times psi of x, y, and z plus the potential energy, which is 1/2 of k1 x squared plus y squared plus 1/2 of k2 z squared times psi. So notice that this is equal to minus h bar squared over 2m times d2 dx2 of psi n x of x plus 1/2 of k1 x squared psi of nx of x times psi of ny of y, psi n z of z. Now the same terms, but for x and y, so we have minus h bar squared divided by 2m times the second derivative with respect to y of ny plus 1/2 of k1 y squared sine y of y. There should be a y here, sorry. times psi nx of x, psi and z of z, plus minus h bar squared over 2m d2 dz2 psi and z of z plus 1/2 of k2 z squared psi and z of z times psi and x of x times psi and y of y. Okay? Notice that this first term here is the energy and E and x times psi of x. So you get that this is equal to the energy E and x times psi and x, psi and y, psi and z. That's just the whole psi of x, y, and z plus ny E and z times psi, E and y, psi of x, y, and z plus E and z times psi of x, y, and z. So this is just the sum E and x plus E and y plus E and z psi of x, y, and z. Now notice that the energy E and x, as I said before, is h bar omega nx plus 1/2 omega 1. E and y is h bar omega 2 times ny plus 1/2, while E and z is, this should be an omega 2, not omega 1, because k is the same for x and y, and for nz it's h bar omega 2 nz plus 1/2. Okay, so in the end, if this is equal to the energy times the wave function, then the energy is equal to E and x, which is h bar omega 1 times nx plus 1/2 plus E and y, that's h bar omega 1 ny plus 1/2 plus E and z, that's omega h bar omega 2 nz plus 1/2. So this is equal to h bar omega 1 times x plus ny plus 1 plus h bar omega 2 nz plus 1/2. This is the energy. Okay? And in question B, we have to find the ground state and first excited levels of the anisotropic three-dimensional harmonic oscillator. So the ground state will happen when nx equals to ny equals to nz. This is the smallest energy possible. So the energy will be equal to 3 h bar omega over 2. This is the ground state energy. While the first excited level, here it's a little trickier than in the previous exercise because omega 1 is equal to the square root of k1 over m, while omega 2 is the square root of k2 over m. Now notice that k1 is greater than k2, meaning that omega 1 is greater than omega 2. Okay, this means that the contribution of energy of the x and y coordinates, that is this first term here, is greater than the contribution of energy for the second term, the term that comes from the z coordinate. So the first excited level, the one that's immediately above the ground state, will happen when nx and ny are equal to 0, but nz is equal to 1. Notice that if nz is equal to 0, but nx is equal to 1, for example, the energy will be greater. So the ground state happens exactly at this state. Okay, so this is the first excited state. And the energy, in this case, is equal to 5/2 of h bar omega. And in question C, we are asked how many different states there are for the ground state there and for the first excited state. For the ground state, there's only one state. That's nx equals ny equals z equals 0. And for the first excited state, there's also only one state. That's nz equals 1, nx equals 0, and y equals 0. Notice that, as I said before, neither nx nor ny can be 0. It can be 1, because the energy would be greater than the energy of the state that has n z equals 1 and x equals 0 and ny equals 0. Okay, this is different from the previous problem, since the first excited state is non-degenerate. Before, we had three possible states that had the same energy, the energy of the first excited state. So before we had nz equals 1, nx and y equals 0, but we also had the possibility that nx equals 1 and z equals and y equals 0, or ny equals 1 and z equals and x equals 0. And that happened because there was an isotropy. So it didn't matter what direction you looked at, the system looked the same, if whether it was x, y, and z. But now there is an anisotropy, meaning that one direction is privileged. In this case, the z direction is privileged, and that's why there's only one possible excited, first excited state, which concludes our exercise.